All right, guys, yesterday we talked about the ideal gas law. This is page 5. Page 5 in your notes. So PV equals nRT. You'll get it in a few minutes. All right. There's always a song, Zach. There's always a song. PV equals nRT, ideal gas law. When you're not given two sets of conditions, like P1, V1, T1, and P2, V2, T2, guys, this is how we figure it out. All right? Gas constant, you should have written it down. For those you guys who were absent yesterday, make sure you get this value down on your reference packet. Write it down right now. It's 0.0821 liters times atmospheres divided by moles times Kelvin. What's that? It's in your notes, but not in your reference packet. Okay? It's not in your reference packet. So, we did a practice. That was what the homework was on last night. Now, guys, the last thing we're going to talk about is gas stoichiometry. So this should look somewhat familiar. We looked at this part down here back when we did stoichiometry, really back when we did the mole, back in Unit 6, where we related particles and mass. There's a third part to it that's talking about volume. But it's only for gases, which is why we didn't do it back in Unit 6. And it's only when gases are at STP. What's STP? Standard temperature and pressure. So, the conversion factor, guys, is 1 mole of any gas. Doesn't matter what the gas is, every gas at STP has the same volume. 22.4 liters. Okay? It is in your notes. 1 mole of any gas equals 22.4 liters. Again, it's only at STP. If you're not at STP, guys, then it's not going to have that volume. All right? So now we have that conversion factor too, that if we were given particles, we could figure out how much mass is in those particles. We could also figure out how much volume, if it is a gas, that we could figure out. Now, if it's a solid, we can't do it. If it's a liquid, can't do it. But if we're given the number of particles of a gas or mass of a gas, we can then get to volume if we're at STP. If we're not at STP, we use the ideal gas law, PV equals nRT. Let's jump in and do some practice problems here together. All right, so again, this is what we just wrote down, what we talked about. Let's try an example. It says, what is the mass of 98 milliliters of sulfur dioxide at STP? What am I given? Let's start there. All right, so that's my volume is 98.0 milliliters of what? Ooh, what is the formula for sulfur dioxide? SO2. Now, what's another important piece of information here? We want to know the mass, so we're trying to figure out mass. What's another? Yeah, STP, guys. Right away, when you see it's at STP, that means that we can use 1 mole equals 22.4 liters. Does anybody see another problem now that we have? Yeah, we've got to go from milliliters to liters. Oh, that's metric conversion. Oh, we hate that, don't we? Yeah, we do. Now, do you remember which one, when you're dealing with a metric system, which one always gets the number 1? The one with the prefix. So 1 milliliter has how many liters? You can look on table A in your reference packet, and you have it there. Maybe not table A. It's table... Which table is it? Table C. 10 to the minus 3, guys. There are 1,000 milliliters in 1 liter. So really what you're going to do is you're dividing that by 1,000. So we're going to get 0.0980 liters. Now, all we have to do is get it to moles. What conversion factor can we use? Yeah, we can use 22.4 liters. So I'm just going to continue it along right here with a new T-chart. Liters is going to be on the bottom. Moles will be on the top. 1 mole has 22.4 liters. Liters will cancel out. Now, do we want to end up with moles, though? No, what do we want to get to? Mass. So let's add another T-chart. You can make it separate ones if you want, but we can just do this. Mole on the top, mole on the bottom, grams on the top. 1 mole. How do we figure out the grams? Molar mass, right? Add it up. We've got SO2, molar mass equals Add them all up. We've got 32 plus 32 equals what? Grams per mole. So there's our conversion factor, 64 grams over 1 mole. Do the math, guys. How many grams of sulfur dioxide do we have in 98 milliliters? Tony? How many sig figs should we report our answer to? 3. Why 3? Look at your original number. 98.0. They are all significant. So we're going to report it to 3 sig figs. How many is that going to be? 0.0280? 0.280 is what you said? There we go. Add STP, guys. It's just conversions. It's using the T-charts. When you're at STP, when you're not at STP, that's when you have to use PV equals nRT. I want you guys to try the U-try problem. Again, STP, guys, is the key piece because if you see that, you know right away, hey, it's just a simple conversion problem. We don't have to use another formula. We can just use our T-chart. So, what do we notice as well about this? We've got to go from milliliters to what? Liters. So, 1.33 times 10 to the 4th milliliters of oxygen. Now I'm going to make one long T-chart. Okay? We can get this to liters. So mils on the bottom, liters on the top. 10 to the minus 3, 1 milliliter. All right? Let's continue on. We can say 22.4 liters to 1 mole. From there, we can do 1 mole on the bottom, and then our molar mass, which is about 32 grams per mole of oxygen. When you do the math, what do you get for a final answer, guys? 18.9 grams. Now, how many sig figs should we have? 3. Because our original number had 3 sig figs in it. So if you round to 19, you're okay, guys, if you round to 19, unless they asked you or if I asked you 4 correct sig figs. So that's why we're kind of going back and reviewing it a lot in this unit. It's an easy unit to do that. Questions? Is this really anything super hard? No, right? It's not too bad because it's just taking our T-chart that we've used and looking at that relationship. Let's take a look. Let's skip this one. Do you guys have this one in your notes? No? All right, we're going to skip over that one. I will. Yep, we're going to get the song in just a minute. I got to build it up, you know. Got to build it up to build that anticipation so you guys are like, yeah, this is awesome. All right? Now, if we're calculating, guys, the density of a gas at STP, it's super easy. What is our density formula? D equals M over V. So what we can use if we're at STP is we can use molar mass divided by molar volume. Which, again, to get our molar mass, we add it all up. Molar volume at STP is 22.4 liters per mole. Okay? Simple. Do you think we're at STP a lot? Are we at STP right now in this classroom? Absolutely not, because you guys tell me how cold it is in here. Well, it's not cold as STP, because what's STP's temperature? Nope. 0 degrees Celsius, which is freezing, like 32 degrees Fahrenheit. So it's cold in here, but it ain't that cold. All right? So very rarely are we actually at STP. So if we can use this, that's great. That makes our work a lot easier. All right? If we're not, though, we use this formula. Okay? D equals PM over RT. D equals PM over RT. What does D stand for? Density. P is going to be, capital M is going to be what? Molar mass. R we know is our gas constant. And T is going to be in what? Okay. So, we can use all those pieces, guys, and then it's just algebra from there, solving for your unknown. All right, so what are we looking for in this problem? Density. That's going to make it a little easier. We don't have to rearrange our equation at all. What am I given? We'll think about that in a second. So what else am I given? Pressure. What is pressure? 800 torr. Now, Jill asked you a question. Does pressure need to be at a certain thing? I'm assuming she means at a certain unit, right? Yeah. Does it? Why? Why did it have to be ATM? Because it'd be weird.
It'd be a really big answer.
It would be a
small answer.
Right, okay, so it'd be weird, it'd be really big or small, but there's a better answer than that because of R, guys. R is our gas constant, 0.0821 liters times atmospheres over moles times Kelvin. That's the reason why we have to get it to atmospheres. How do we do that? Yeah, divided by 760. Somebody do that math really quick. 800 divided by 760. What do we get? What's that? 1.05 atmospheres. All right, what else am I given? Temperature. What do I have to do with that? Add 273. That gives me 298. Notice that's one that we use a lot. We've seen it in a lot of problems because, hey, it's kind of like room temperature, so it's a common temperature. What else am I given?
The formula.
Okay, so I've got the formula D equals P capital M over RT. Do I have everything I need in that formula? Yes, how, Alex?
We take the compound and find its molar mass.
Absolutely, guys. We're going to find the molar mass because we are given the compound right here as NH3. Nitrogen is 14 plus 3 is about what? 17. Now, should you guys round like I just did? No. On your test or quiz, you're going to go to your periodic table, add them all up. For the sake of time, we are going to round. Okay? All right, now it's just plug and chug from here. It's super easy. So we've got 1.05 ATM multiplied by 17 grams over mole, all over our constant, 0.0821 latum over molk. And we have our temperature, which is 298 Kelvin. So Kelvin's going to cancel out. Moles will cancel out. Atmospheres will cancel out. So what am I left with my unit? I know it's hard to see. We have grams and liter. Oh, is that a density unit? Yeah, absolutely. That's a good density unit. Mass per unit of volume. So all you guys have to do is do the math. Simplest way is to take 1.05 times 17. Then on your calculator, hit divide by 0.0821. Divide by 298. It's the least amount of keystrokes. If you do it, you will get the right answer every single time. Who can tell me what our answer is? What's our density of this gas? 0.73 grams per liter, because 2 sig figs is what we have for our temperature. Easy? Again, it's just another formula. So that's the hardest part, guys, within this unit, is identifying what pieces you have and what formula you're going to need to use. That's the hardest part about this. But if you write down all of your variables that you're given, it can make life a whole lot easier to start to pinpoint which formula you're going to use. Questions? All right, let's take a look here. All right. This is where we start getting into some mixed problems. And this, I believe, is back on page 6 in your notes, if I'm correct. All right, it's the first example there. It says, how many liters of oxygen are required to react with 0.35 liters of propane at STP? So we may have to use molar volume, or we may only have to use molar volume when? When can we use molar volume? At STP, okay? We may have to use the ideal gas law. When would we do this? Or use the ideal gas law? When there could be one of each pressure or volume. Even better answer though. Similar to the other answer we just gave. When it's not at STP. Okay? So when we're at STP, we can use molar volume. When we're not at STP, we have to use the ideal gas law. What are we at here? STP. So what can we use? Molar volume. That's just a T-chart conversion. Now, let's say you forget about that. You can always use the ideal gas law. It's a little bit more work because you've got to, plug into the equation and solve for it instead of just doing a T-chart conversion, but it will always get you to the same answer. Go ahead and do this problem. With this problem, guys, we will use our T-chart because this is stoichiometry right here. Okay? We're going from one substance to another, so we have to look at the mole ratio. So since they're both at STP, they're both gases that we're looking at, we're just going to go from liters of one to liters of another. Just like we did grams to grams. It's the same idea. Propane, C3H8. Since we are at STP, guys, we can use molar volume. Our value for that, again, is 22.4 liters per mole. So here, we've got liters, so we can get that back to moles. Okay, that's gone there. Now we're going to use our mole ratio. So we have moles of C3H8 to moles of what we're trying to get to, which is oxygen. Where do I get the numbers for my mole ratio here in this fraction? Where in the equation? Specifically, they are the what numbers? The coefficients, right? So propane is a 1, oxygen is going to be a 5. And then over here, we're still going to have 1 mole of oxygen is 22.4 liters of oxygen. So really, guys, the 22.4 liters is going to cancel out. All we're doing is we're taking 0.35 and we're multiplying it by 5. What do you get for an answer? How many liters of oxygen would be required? 1.75. Bam. That is a review with a new piece, a little new twist from our last unit, or not last unit, from Unit 8 with stoichiometry. Questions?